Okay, so now we're going to talk a little bit about antiderivatives. When we go through the process of recovering a function, say capital F, from its derivative little f, this process is called antidifferentiation. All right, so we're using the capital F to represent the antiderivative of a function. Right, and so what this means is we've been focusing on taking derivatives for so long. So suppose I give you f of x equals 2x. All right, and I said, well, tell me what that was before you took the derivative of it. And so if we try to recover that original function, we might call that capital F of x, which could be x squared. All right, so capital F represents that antiderivative. We could do something similar for, say, cosine. So if I had f of x equals cosine x, what was cosine before you took the derivative? And what we know is that that is sine. So we can check this by going in the opposite direction. And what I mean by that is that I know the derivative of sine is cosine, and I know the derivative of x squared is 2x. But what we have to think about now is, going from that f of x equals x squared back to 2x. Is that the only function, f of x equals x squared, that has the derivative of 2x? So if I look at derivatives, right, as opposed to antiderivatives, going in the opposite direction, derivatives, if I took the derivative, if I have f of x equals x squared plus 10, wouldn't I be able to say that f prime of x is 2x? And what if I had f of x equals x squared minus 3? That would also be f prime of x is 2x, right? So what do we notice about these three functions? X squared plus 10, and x squared minus 3. They all have the same derivative. The derivative of x squared plus any constant is always going to be 2x because the derivative of a constant is 0. So this leads us to another important thing to think about. If we have a function, capital F, representing an antiderivative of little f on some interval I, then the most general antiderivative of f on I is going to be that antiderivative plus c. And what c represents is an arbitrary constant. And so what we can see here, if I had all of these different functions, y equals x cubed plus some constant c, and that constant being 2, 1, 0, -1, or -2. All of those different arbitrary constants, if I were to take the derivative, let me write that properly here. If I said y prime, I would get 3x squared, and the derivative of that constant would always go to 0, which we wouldn't write. So, all of these different functions, y equals x cubed plus 2, y equals x cubed plus 1, y equals x cubed, y equals x cubed minus 1, and y equals x cubed minus 2. All of those functions have the same derivative. So that's because when we take the derivative of a constant, it goes to 0. If we think about this in the reverse direction, when we do antiderivatives, we have to assume there was some arbitrary constant there that we took the derivative of and got 0. Okay, so as we start moving through this antiderivative process, we're always going to be adding plus c at the end of our antiderivative work, because we're assuming there could have been a number there. I mean, c could be equal to 0. And as we progress through this section, we'll talk about finding that exact c value if we have some initial condition that is set within the problem. So now that we kind of have a general understanding of what an antiderivative is, it's the opposite of a derivative, let's define our first rule, which would be the power rule for antiderivatives. So, if little f equals some x value raised to a power n. And in this rule, n can be any number except n cannot equal -1. And we'll talk about why we can't have -1 be that exponent power. So if this is the function and we want to find the antiderivative, like think about we have a little function and we're using this capital F because it's the parent, right? It's what it was before. So what we are going to do is the opposite of finding a derivative. And when you think about a derivative, we're going to always take that exponent, we multiply it in front, and then we subtract 1 from the exponent. So instead of subtraction, we're going to add, and instead of multiply, we're going to divide, but we're going to do them in the reverse order. So my process here is to first add 1 to that exponent, and whatever that is, then I'm going to divide by that new exponent power. And then, of course, we're always going to write plus c at the end. Okay? And whenever you're doing these antiderivatives, once you get your answer, remember, you can always check by taking the derivative, which you should feel very comfortable with at this point. So let's do an example here. Let us find the antiderivative for f of x equals x to the 5th. So this exponent can be any number, it just can't be -1. So in this situation, when I go to find my antiderivative, capital F, I'm going to take that x, I'm going to add 1 to the exponent, which is going to give me 6, and that 6 value goes into the denominator. And of course, we write plus c. So simplifying this, my antiderivative f of x equals x to the 6th over 6 plus c. And we can clean that up a little bit. I could say, well, that is f of x equals 1/6 x to the 6th plus c. Okay, so here is my antiderivative. Remember, we have to write plus c because there could have been an arbitrary constant there. We're just not sure. So if I go to check this, f prime of x, well, remember the 1/6 stays, and when I take the derivative of x to the 6, I multiply by 6, I subtract 1 from that 6 in the power, gives me 5, and the derivative of a constant would be 0. So what you can see here, the 6 and the 1/6 cancel out, the 0's gone, and our derivative, if we were looking to go the opposite direction, would be x to the 5th. All right, so we checked. So let's continue this with one more example. We're going to find the antiderivative. We're going to find the antiderivative for f of x equals 3x squared. And we're given an initial condition. We'll say that satisfies the fact that f of 1 equals -1. All right, so finding that antiderivative using our power rule we've just defined, f of x, capital F, We'll leave that 3 there. I'm going to take this x squared. I'm going to add 1 to the exponent and then divide by that value, 2 plus 1. And then remember, whenever we're doing an antiderivative, we always write plus c. So if we simplify this, we've got f of x equals 3x cubed over 3 plus c. We can see that the 3's will cancel, and f of x equals x cubed plus c. So now what we need to consider is that in this situation, we're given what is called an initial condition. And if we have that initial condition, then we can determine what that c value actually was. So we know that y is 1, negative 1, when x is positive 1. So this is like giving us an ordered pair, 1, negative 1. So negative 1 equals 1 cubed plus c. Negative 1 equals 1 plus c. If I subtract that 1 from both sides of my equation here, I get that c, negative 2 equals c. So my answer is f of x equals x cubed minus 2. So we were using an initial condition to determine what that c value is. So we kind of understand the concept of antiderivatives. And we have lots of rules or properties which we'll use for antiderivatives. In fact, there are tables of thousands of antiderivatives, right? And as we move forward, we call these antiderivatives integrals. So we're building towards our knowledge of integration, okay? And we've talked about one rule of integration, our power rule of integration, which you guys should all feel comfortable with. It's just the reverse of our power rule of differentiation. But real quick, I like to talk about why on that power rule we had to specify that my n, my power, can't be negative 1. So my power rule again said if I have f of x equals x to the n, then my antiderivative, capital F of x, x to the n, is x to the n plus 1 over n plus 1 plus c. And so why can n not equal negative 1? Well, f of x being x to the negative 1, that's the same as f of x equals 1 over x. So let's go back and think about derivatives here for a second. What is the derivative of natural log of x? 1 over x, right? So you would then say, if we thought about antiderivatives or integrals, which we're building towards, if I have f of x equals 1 over x, then my antiderivative, capital F, is going to be the natural log of x plus c. Okay, so when we think about an antiderivative, if that exponent power is negative 1, then we know that the antiderivative, it was actually the natural log to begin with. So, and we'll do more examples with that later. I just like to point out that our power rule works for anything except for when that exponent power is negative 1. Okay?